Hi, my name is David Fox, and I am happy to introduce our design concept for NASA's Breakthrough Innovative and Game-Changing Idea Challenge. Our design is LETO, Lunar Dust Mitigating Electrostatic Microtextured Overlay. The upcoming Artemis missions will feature long-term habitats near the lunar South Pole in preparation for the missions to Mars. These missions still have an unsolved issue dating back to the Apollo missions, which is the spacesuit integrity after exposure to lunar dust. The lunar dust poses significant issues for the upcoming Artemis missions. It is fine with sharp edges and can wear down the suit materials, as well as many significant other issues. The tracking of dust into the habitats on the lunar surface may pose health risks to the astronauts, and the mission lifetimes are planned to be significantly longer than the Apollo missions, perhaps weeks at a time. We looked to nature to see if there was any solution for transferring small particulate matter. Pollen, which is on the micron scale, seemed an appropriate model for the ultrafine lunar dust. The methods in which pollinators, such as bees, are able to transfer pollen to flowers has been proposed as a combination of the fine surface microstructure on the bees as well as the local electric field around the bees and flowers, which are generated from static electricity as well as Earth's natural electric field. The bottom left image shows charged powders of dye being placed onto a flower where it selectively deposits onto the tips and edges of the petals where the distortions in the local electric field are. Our design concepts borrow from nature and use material engineering to bridge electrostatic charging and the small microstructures. During the Apollo missions, it was noticed that the dust appeared to self-levitate, overcoming the gravity and contact forces due to charging on the surface of the dust. We thought it was best to explore these forces during our research and design. Many forces or environmental factors can affect dust clinging to surfaces. Through our literature review, we noted that the small particulate matter around us can teach us about dust interactions. For example, the differences between how rice or flour can be poured is an example of grain interaction dependent on grain size, or how small quantities of water may strongly affect adhesion, such as in the building of sandcastles. We thought it was best to focus on the charging of the dust as these aligned with our design goals.
Electromagnetic radiation and plasma ions are among the fundamental sources of electrostatic charging on the Moon's surface. There exists a shifting balance between positive and negative charge that is dependent on direct irradiation from sunlight. The photoelectric effect describes the emission of electrons from a material upon exposure to electromagnetic radiation of sufficient energy. The formula seen here shows that kinetic energy of the ejected photoelectron scales with the binding energy of said electron. Constant bombardment by the sun's light emits photoelectrons to leave a net positive charge on the surface during lunar day, whereas the lunar shadow experiences no such effect and consequently accumulates negative charge from plasma electrons. To better simulate lunar conditions, we required a light source of sufficient energy to charge the lunar dust simulant. It is known that emission from hydrogen is of greatest intensity on the Moon's surface, with a wavelength of 121.6 nanometers. We used a readily available helium lamp that serves as the source for ultraviolet photoelectron spectroscopy. As expected, the low-energy light did indeed eject the electrons from the insulating dust surface, as evidenced by the broad peak liberating a range of electron energies. This result inspired more stringent testing conditions, so we ordered a 121 nanometer hydrogen source lamp that will be used in conjunction with vacuum to provide a high-fidelity testing environment. Details of this future testing will be expanded upon later in the presentation.
So our proposed solution is to use a lunar dust mitigation electrostatic microtextured overlay, or LETO for short. There will be three major components. First, there will be macrostructure, microstructure, and then there will be electrostatic charges. All of them will contribute to the overall LETO design. Now you may be wondering, where does the word LETO come from? Fun fact, is actually the name of the mother of Artemis and Apollo, and we know that these names are also the names of the NASA space programs. Now for the LETO design, we're planning to put this over the current spacesuit, and it's going to have an origami macrostructure that's going to help reduce wear and tears. There's also will be microstructures that's going to help reduce dust adhesion and promote passive dust mitigation. And then the overall material is going to be conductive and is going to take up electrostatic charges and promote active dust mitigation. Further details of each of these components will be discussed in the next slides.
One of the components in the LETO design is the macrostructure. This is inspired by origami designs from David Huffman and Koryo Miura with flat-folded or curved crease patterns in the scale of centimeters. By designing a material with such patterns, it alleviates strain as a result of mechanical manipulation, such as stretching or bending, and thus increases the overall lifetime of the material. Different folds and patterns can be used in the overlay for various parts of the body, depending on the type of movement employed. The Miura fold, also known as Miura ori, is a tessellated parallelogram fold which can be compressed neatly into a smaller volume or be stretched out flat without overworking the material. In these examples, curved folding from Huffman was replicated to show that the material can move in different directions with a minimal amount of strain. Using curved creases and patterns are promising in which they can distribute forces more evenly across the material, and we believe that would be the most effective macrostructure. With all this in mind, polymers can be used as our paper element to impart these origami patterns with improved mechanical properties.
The material we selected to utilize as our test polymer was thermoplastic polyurethane, or TPU. TPU is a clear elastomer and was much more straightforward than silicon-based resins used in our early designs. The crosslinks in TPU can dissociate above 80 degrees Celsius, and above this temperature the material can be reshaped and then cooled to retain such a shape. TPU is idealized as a great model polymer to design these experiments before moving to a space-rated polymer such as polyamide. We utilized SolidWorks to design our 3D objects, which were then printed with a Formlabs 3 printer, generating both positive and negative mold faces. The polymer chosen was a high-temperature resin, which can withstand temperatures over 250 degrees Celsius, which is well above the processing temperature for the TPU. Through printing high-resolution designs, it is possible to couple both macrostructure designs and microstructures. Before we highlight this process, we can first go more into depth into the microstructure components, which were obtained through collaboration with Morphotonics. Morphotonics is a machining manufacturer in the Netherlands. They utilize large area roll-to-plate micro and nano imprint technologies to produce scalable flex stamps, which are well suited to our design purposes. The lithography process is shown here, where polymer resin is photopolymerized to generate large area stamps. Control over the optical and wetting properties through the surface structure can be seen. We also thought it would be useful to include a portion of the conversation with some of the researchers and engineers over at Morphotonics to get better insight into their technology.
Okay, so we already seen like the technical aspect of what your equipment can use, but we're kind of curious to know like what type of material are you able to imprint on? Because that's what we're trying to focus on with the overlay, right? So be interesting to know if we can have a variety of things we can work with.
Sure, I think I can answer that. So we have a roll-to-plate imprinting machine, which means we can print on discrete materials up to 1.60 meters long for our largest equipment. And the materials we can print on are all kinds of polymers like PMMA or acrylates, other acrylates, polycarbonate. Glass is a very often chosen material for imprints. And even we can print on metals or functional devices.
We wanted to know, what are some of the other technologies that your material could be applied for?
Some of the other applications that our technology can be applied for are display related and some non-display related applications. And display world, anything that has to do with replicating a nano or micron structure on a large area to reduce the costs and to improve or increase the throughput can be beneficial.
The elastic properties of the TPU can be seen, as well as the ability of the TPU to be given a surface microstructure when heated above 80 degrees Celsius.
As you can see, we were successful in creating these macrostructure molds with different origami patterns to it. You can see with this one has more of a wavy curved crease to it, and this one's a little bit more edgier, and this is from the Miura Ori tessellation. And we can see that upon printing the TPU film with this, we'll have good shape conformity of the patterns. And if you were to fuse these at the ends, you'll be able to stretch it and it would spring back into place without further shape deterioration. So this larger piece has the overall macrostructure pattern, and these smaller pieces has our microstructure patterns. So each of these facets actually has the microstructure film on it. And this little bit of rainbow indicates this is a diffraction microstructure pattern. So to explain a little bit about the printing process, TPU is a thermoplastic, so it would soften and then can be molded and conform to a specific pattern and shape. So upon heating it onto the microstructure pattern, then we take the microstructure pattern mold on and place it on top of the facets, and then you see once we press it together and wait for it to cool, then remove it, you have your sort of final product at the end. So with the final printed film, we can see there's proper transfer of the macrostructure and the microstructure. You can see a little bit of rainbow in the video here from the diffraction pattern. And we know that TPU is an elastomer, so it's able to return back to its original conformation once you compressed it or you stretched it. So another good thing too is that with this material, you can fuse it at the ends and then you can seam it, almost like you're playing with a fabric. So you're able to make these complex shapes and designs and create your overlay according to a specific part on the suit.
In this part of the project, we are measuring the interaction between individual grains of lunar dust and our microstructures using an atomic force microscope, also known as an AFM. Atomic force microscopes are a series of scanning probe microscopes that were invented in the 1980s and is used to characterize mechanical properties like adhesion, friction, dissipation of energy, and also electrical properties like electrostatic forces and magnetic properties. AFMs can perform in high vacuum to fluids, and you can use them to probe and pull in substrates. The AFM typically has three major abilities, which are force measurement, imaging, and manipulation. For this series of experiments, we are using force measurement, which measures the forces between your probe and your sample as a function of their separation. Force measurements produce force distance curves, which allows us to study nanomechanical properties like elasticity, surface charge, and adhesion. And so if you look at the diagram, you see the photodetector that records how the cantilever deflects based on the laser spot. To obtain a single force curve, the base of the cantilever is moved down towards the sample and then retracted from the sample back to the rest position. As a result, you have a force distance curve, which you see on the right, where the x-axis is distance and the y-axis is deflection, which is then converted to force. This is an example of a typical force curve. And so at point A, you are the farthest away from the sample, and as you go to point B, you experience either a van der Waals force, a capillary force, or some force that makes you snap into the surface. And then at C, you're beginning to push into the surface, and and at point E, you're beginning to retract off of the surface, and from G to H, you're pretty much pulling off of the surface completely. And you typically extract the adhesion from point G to H, and the energy dissipated in the interaction is usually by integrating the retract curve to the baseline, and you can also extract the Young's modulus or stiffness of the sample by measuring the slope of the retract curve. To measure interaction between a dust particle and our microstructures, we used a lunar island simulant made by the Exolith lab at UCF and a tipless cantilever with a high spring constant. We used a DEFCON 2-ton epoxy to attach a small lunar regolith particle to the end of a tipless cantilever as shown in the SEM images here. We then use the probe that the grain attacked to acquire force curves in our microstructures. An important note is you can see that the grain has a complex surface with some smoother areas and rougher areas, which ultimately influences our interaction of the grain to the microstructures. There are many factors that influence this interaction at this scale, but an important factor is contact area, which is influenced partly by the roughness of the tip and the substrate. So this is the setup of our AFM. So typically we load our cantilever into the cantilever holder. Then we position the laser spot at the very end of the cantilever because that's where we get the most response. And so then we move our crosshairs in the optical microscope to the tip of the cantilever as shown. Then we make sure our deflection and laser sum is at the max, and green, that means that we're good to go and ready to perform the experiment. And so this is a resultant curve of performing force curves on a flat surface like glass and our microtextured surface. And as you can see, there's a difference between performing on a flat surface and the microtextured surface. And we realize that the forces or the interaction is weaker on the microtextured surface, typically because of contact area and because of the roughness of the tip and the sample in combination.
We looked at the lunar dust on different microstructures through electron microscopy to see the appearance and distribution of the persistent lunar dust. The dust clings firmly to the sides of the pillars. The top images shows the dust on the 15 micrometer sized pillars, and the bottom right image shows the dust on 2 micron sized pillars. To function as the honeybees, we thought it would be best to utilize the 2 micron sized pillars for further testing. Abrasion testing was performed on the microstructures using lunar dust for certain time intervals, using a constant pressure of 5 psi. After 3 minutes, the structures still remained on the surface, as compared with the orthofabric, which shows the fiber structure beginning to break down. We thought it was worth testing certain microstructures which are compatible with so-called self-cleaning technologies. By applying a surface texture to the TPU of 5 micron ridges, the hydrophobic nature of the surface was increased, and water droplets may bead up and roll away from the surface. When these water droplets roll off, they carry much of the dust away. We thought this design consideration was worth noting before we bring attention back to the combined studies of electrostatics and microstructures.
After considering the microstructure and the ability to limit the interaction between the particle and the surface, we face the challenge of repulsion, or overcoming the attractive forces that are still present. Adhesion or attraction between two objects becomes a bit more complex on the microscopic level. The fine particles of dust adhere to the lunar surface under the influence of both gravitational forces and van der Waals forces. While we've grown accustomed to the effects of gravity, van der Waals forces create attraction through short-range electrostatic forces between two molecules. We need to take into consideration not just size and distance, but factors like surface layer thickness and material density. One variable that encompasses these parameters is the Hamaker constant. It's represented by H. It describes particle interaction, and its magnitude reflects the strength of the van der Waals force. In this case, it's indirectly proportionate to a certain molecular diameter, allowing the variable K sub S to be proportionality constant in the first equation seen here. These equations help us to quantify the forces in order for us to determine a better understanding of the charge needed to overcome them. Van der Waals forces are determined when looking comparatively at the thickness of the layer of adhered material to the size of the particle in question and the roughness associated with the surface, represented by beta. Through this quantitative analysis, we can determine that greater roughness significantly reduces adhesivity, further concluding that the larger the particle becomes, the weaker the van der Waals force. and gravity becomes the prominent force as the particle radius size becomes larger. If we look at the graph here, we can see that van der Waals forces start out at a higher force magnitude for smaller particle size compared to gravity. And as we continue to follow the graph trend, we notice the changes in beta and its effect on the overall force, and also gravity catching up and increasing exponentially as the particle size gets larger. The effect of the collective forces needs to be overcome by the very own electrostatic force acting between the two particles and the surface measured in coulombs.
The engineering problem of overcoming the various attractive forces holding dust particles to the surface of the spacesuit led the team to look for a way to safely establish a high electrostatic charge on the surface of the material to repel charged dust particles. Tribocharging is the effect of electron transfer between certain materials when made to contact. This charging can be increased by rubbing, like walking across a carpet in wool socks, or a fur rubbed across a glass rod, generating enough charge to be felt by hand. Many electrostatic generators take advantage of this physical occurrence. The most familiar to us all, from science museums and physics class demonstrations, is the Van de Graaff generator, a mechanism capable of building several million volts of potential on the surface of a conductive sphere. The Van de Graaff generator was invented in the late 1920s for application as a particle accelerator in nuclear research. These contraptions vary in scale, but all consist of an insulating, often rubber belt, spinning between two rollers. One of the rollers is connected to a motor, and the other is placed within a hollow conductive metal sphere, insulated from the rest of the contraption. As the belt spins, electrons transfer from the grounded roller to the belt through triboelectric charging, and the belt polarizes to have a positive and a negative side, a property known as dielectric polarization. The belt then transfers the electrons towards the upper spherical electrode. Since the charge is deposited on the inside of the sphere, it acts as a Faraday pail, and through electrostatic induction, the charge is distributed across the outside surface of the shell. This property allows for such a high voltage to develop on the top electrode without the induced field repelling the flow of electrons through the belt. The maximum voltage generated by Van der Graaff generators is limited by the insulation between the positive and negative electrodes, and by the radius of the sphere. Corona discharge will also leak charge to the surrounding atmosphere at high enough potentials. Some of these downfalls can be controlled by containing the generator in a vacuum or an insulating gas such as sulfur hexafluoride. Belt speed also affects the charge on the surface as it counteracts the loss rate of charge. While voltage generated is high due to the large difference in charge, the current is too low to cause harm to humans. The composition of the rollers affects whether the electrode develops a positive or a negative charge. The rollers are made from different materials, ideally on opposite ends of the triboelectric series. A material falling on the positive spectrum used as the top roller material will cause a positive charge to build up on the electrode. Switching this to a material on the negative end of the series will cause a negative charge to build up. We constructed a benchtop Van de Graaff generator using a nylon upper and Teflon lower roller to measure how much charge could be produced at a small scale. The device was capable of generating several thousand volts, and with improved components and design allowing a higher motor speed, it could generate much higher. Modern improvements on this design use a chain of metal pellets instead of rubber belts to carry a higher charge between the terminals. Now, let us look at how to incorporate conductivity into our spacesuit material to make use of this charge.
Now, in order to pick up the electrostatic charges, the overlay has to be conductive. The polymer on its own is insulative, so we decided to integrate metal nanowires to the material. Nanowires polymer composites are well studied in the development of transparent and flexible conductive devices, concerned that the long and thin structures have nanoscale diameters and micron-sized lengths. We use core shell silver and gold nanowires as our conductive nanofillers. Now, silver nanowires are commonly used due to its high conductivity, low cost, and ease of processing. However, they tend to easily oxidize over time, reducing the stability of the wires and thus diminishing the functionality of the conductive composites. Now, gold is highly conductive and is chemically inert, so by using a well-controlled deposition reaction, we can put a gold shell around the silver nanowires as depicted here in the image. As seen in the graph, the sheet resistance of the silver nanowire coated film increases over time, whereas the one with the core shell seems to have little change in the resistance, thus proving that the gold shell deposition improves the wire stability and overall composite longevity. Now with the generated nanowire pattern film, we saw that the wires are distributed in a successful network between the groups and some on the macrostructure. Now one key thing to keep in mind is that the deposition of the wires should be done on a flat TPU film prior to imprinting the macro and microstructure pattern to ensure that the wires are embedded in the surface and pattern of the film. We did a test with a simple electric circuit connecting a voltage supplier, LED light, and our nanowire TPU film. Firstly, with a flat conductive TPU sample, the LED was on, but upon stretching the material, the LED would fade and go off as the conductive network was being broken. And bending seemed to have the same effect. Luckily, after the material springs back to its original conformation, the LED turns back on. But for a conductive overlay, having such a decrease or loss of functionality when mechanical manipulation was being applied can mean unsuccessful overlay charging during active dust mitigation. Now with the LETO design TPU sample, we first saw that there is successful LED function. And then when you stretch it to a flat conformation and then back to the folded, there was little change to the LED, and this demonstrates the conductive network was still intact after manipulation.
The test was performed with and without vacuum UV lamp source in the event that some charging could occur through ionization of air molecules around the dust or otherwise. However, as was expected, there is no difference noted during the dust removal process through this method. Further testing in vacuum will be attempted, and the vacuum UV light source may cause charging in that case. A gold coating, sputter coating, was applied to the sample to ensure that the charge was distributed evenly as possible during the testing. By applying a high voltage across a 3 centimeter gap, the field strength was sufficient to cause larger dust particles to be ejected from the surface. The video shows the voltage being adjusted from 0 kilovolts to 20 kilovolts. Many of the more persistent dust particles still remained, likely due to their lack of any kind of native charge. Using particle tracking software, the images may be extracted and converted to 8-bit images, with thresholding applied to only visualize the highly reflective lunar highland simulant. The histograms can be seen on the right with the selected regions outlined. Additionally, SEM images were obtained at several magnifications to highlight the size and density of the persistent dust. It was noticed that much of the dust on the same scale as the microstructure appeared absent, potentially due to the electric field distortions around the individual microstructures.
Hello. In this slide, we are showing the Terra Universal acrylic vacuum chamber that was used for component testing as well as concept checks. In the left image, we can see the robotic arm that was used for vacuum testing, as well as the vacuum setup where we had one feed-through into both air and the vacuum pump. The right image shows the vacuum gauge as well as the two electrical feed-throughs. These feed-throughs were made in the lab using epoxy resin as well as high gauge wires. These wires had a resistance between one another in the mega ohm range, and as such a second feed through was made so that we could also potentially perform high voltage testing. Due to the time required in order to design and assemble this vacuum chamber, not all the tests were performed here. We required a higher quality vacuum chamber in order to continue software testing. The previous vacuum chamber had insufficient space for some of our testing components. As you can see, the newer vacuum has quite a bit more space. Also, our new Hamamatsu lamp with Lyman alpha spectra had arrived and could be installed into the new bell jar, which was in collaboration with Dr. Brissett at Florida Space Institute. The new vacuum chamber could be used to conduct many additional testing. Our team would like to thank our collaborators, as well as NASA's Big Idea Challenge team, for their support, as well as you for watching. Thank you very much.